instead of two categories of colors, we have 8, right? How would a clustering algorithm likely interpret this? I would look at each candy and make the following conclusions. Each candy is in its own color. So as an algorithm, without special training, it doesn't know the relationship between colors. For example, unlike human eyes, I do not know that the pink is closer to red than turquoise. So given this set of features, I conclude that there are 8 clusters and they are all equally similar to each other. I also conclude that out of 8 clusters, 4 are spicy and 4 are sweet. So because of this, many kind of misinterpretation leads to serious problems like loss of grouping ability, inability to generalize, and wrong predictions. The model cannot form meaningful clusters because all features seem equally distinct, and inability to generalize. A new candy of an unseen color will confuse the model. It won't know where to place it. So wrong predictions may happen. Since all the clusters are equally similar, the algorithm might randomly assign spicy or sweet. Thus, even though we added more data or more colors, our model's performance decreased the exact opposite of what we expected. This is a perfect example of how the curse of dimensionality manifests in real world problems. So, dimensionality reduction to the rescue. To fix this, we apply dimensionality reduction, a mathematical technique that captures the essence of the data using fewer features. So in our candy example, we realize that all colors can be represented using just two hidden variables, red exposure, blue exposure. So every color, whether it's a maroon, pink, turquoise or ocean, can be expressed as a mix of red and blue intensities. By converting the data into these latent features, we reduce 8 color features into 2. So simplify the data set. Restore relationships between similar colors like pink is equal to red, and at the same time turquoise is equal to blue, and it can be considered it is equal to blue. Ocean, it is considered to be equal to blue. Likewise, it can be considered. Now the model understands that candies closure in red-blue exposure have similar properties, effectively rebuilding meaning from complexity. So this can be applied for the simplifier. Here, what is the new model does? It records each candy's color, transforms that color into two numerical values, red exposure and blue exposure, plots candies in a two-dimensional space where the x-axis is red and the y-axis is blue, calculates equilibrium distance between candies to find the nearest cluster. So these things has to be done. So assigns labels. Candies near the red cluster can be labeled as spicy. Candies near the blue cluster can be named as sweet. This process makes the model interpretable, efficient and generalizable, exactly what we want in machine learning. So this is what the application of the simplified model. So this shows you the exposure of blue as well as red. Once dimensionality reduction is applied, the clustering process becomes straightforward again. Here is what the new model does. It records each candy's color, transforms that color into two numerical values, and those numerical values can be named as red exposure and blue exposure, plots candies in a 2D space where the x-axis is red exposure and the y-axis is blue exposure, calculates Euclidean distance between candies to find the nearest cluster. So now we assign the labels. Candies near red cluster or spicy, and candies near blue cluster is named as sweet. This process makes the more interpretable, efficient and generalizable, exactly what we want in machine learning. So the final visual shows the candies distributed in a 2D plane. The x-axis shows red and y-axis shows blue exposure. Now two main clusters emerge clearly, red cluster and the blue cluster. So red is considered as the spicy one and blue is considered as the sweetest one. Instead of 8 meaningless clusters, we now have 2 well-defined ones. The data has regained structure and the model has regained sense. This demonstrates how reducing dimensions can make data both simpler and more powerful. So the course of dimensionality teaches us a vital lesson. More features do not always mean more knowledge. In fact, beyond a point, they can obscure relationship, confuse algorithm and inflate computations. Dimensionality reduction techniques such as principal component analysis finds principal components capturing maximum variance, and T-distributed stochastic neighbor embedding preserves similarity for visualization. Autoencoders, neural networks that learn compressed, meaningful representation of data helps us overcome this curse. By reducing unnecessary dimensions, we make AI systems faster to train, more accurate on real world data, and easier to interpret and visualize. So this is how the dimensionality reduction converts complexity into clarity, helping us turn vast data spaces into actionable intelligence, the true goal of artificial intelligence.